Welcome to this second video on Maxwell relations. Now in this second video we are going to derive the Maxwell relations. You remember in our last video we are looking at various Maxwell relations and how you can be able to remember those Maxwell relations. I give you a very simple statement which you can be able to use to remember the Maxwell relations, the four Maxwell relations that we looked at. And I hope that from where we left, you have continued to be able to get the other Maxwell relations that I did not finish up in that video. So in our today's video, we are going to be able to derive Maxwell relations. And the Maxwell relations, you can be able to derive it using the other mechanical relations that we have seen in relation to Maxwell relations. For example, you can use the Gibbs relation, you can use the Helmholtz relations, you can use the enthalpy relation, and so on and so forth. But for today, we are going to see the relations when you're using the Gibbs free energy. And Gibbs free energy, you remember very well, is given by this equation: dg is equal to v dp minus s dt. And you're going to call that one as our equation 1. And I want you to consider this case whereby the Gibbs free energy is given under the condition of pressure and temperature. Those are the two conditions that to consider when you're looking at the Gibbs free energy, when you're varying pressure and temperature. So, given that is the case, this equation we can differentiate it by parts. And when differentiated by parts, we have dg dp, so we have dg dp, and temperature is kept constant, and we're differentiating with respect to pressure, and then we differentiate with respect to temperature, so we have dg dt, as you can see there, and then we keep the pressure constant, so with respect to temperature. So this one we call it our equation 2. So we have this equation and this equation. The two equations are defining the same thing. They are defining the small change in Gibbs free energy. That is dg here, dg there. The only difference is that the constant that are involved. Now, since we are defining the same thing, we can be able to equate this one and this other one here, because both of them they are defining the Gibbs free energy. So when we equate this one and this one, this is what we are going to get here. So you have dg dp dt, dp there, and this other one here is equal to this. Now, I want you to look at the coefficients. Look at the coefficients here for dp. The coefficient for dp in both equations, you can see that the coefficient for dp here is dg dp, pressure temperature constant. Now this one is the same as this other coefficient because the two equations are the same. So this coefficient here is equal to this, and that is why we have this equation here: dg dp at constant temperature is equal to v. Then look at this other, the coefficient for dt in both cases. So the coefficient for dp here we have dg dt at constant pressure is the same as this one here, negative s, and that is where we derive this other equation that you can see here, that dg dt at constant pressure is equal to negative s. So we come up with two other equations from what we have there. So this one you can say this is equation A and this one is equation B. So we starting with the equation here, we can start by differentiating again so that we can get the second derivative. So we differentiate, remember we had the first derivative there, so this is now when you differentiate again you get the second derivative. So we differentiate this now with respect, because we differentiated first with respect to t, with respect to p. Now we are going to differentiate with respect to p. In the other one we kept t constant, so here we are going to keep p constant. So this is what we are going to have. we are going to have, we're differentiating, so we have d dt, keeping the pressure constant, because here we had temperature constant, so you keep up the pressure constant, and this portion, which is this, remains as it is. It remains as it is here. So you only add d dt pressure constant. So this one is the same as, on this other side, we differentiate the V, or the volume, with respect to T. So that is where we have dV dt. But remember, it is the pressure that we are keeping constant this time, because the other part, the derivative, we kept the temperature constant, so the pressure is kept constant. Now, so for the second, for equation A, obtaining the second derivative, this is what we are going to get. For equation B, remember here, we differentiated with respect to T in the first, to get the first derivative. So that means the second derivative, we will differentiate with respect to P. In the first derivative, we kept P constant. So in the second derivative, we are going to keep T constant. So that is what we have here. So we are saying that to obtain this one, so we are going to have dP. So we're keeping T constant, because in the first derivative P is constant. In the first derivative T is constant. P is constant. So in the second derivative, we reverse. T is the one which is going to become constant. So we differentiate the first derivative, we differentiated with respect to T. So in the second derivative, we differentiate with respect to P, because you can't have the differentiate two at the same time. So when you differentiate this one, so we are going to have d dP, temperature constant. This first derivative remains as it is equal to, so you see it's negative. Here we have negative ds, so we differentiate with respect to P, so we are going to have ds, negative ds dP. So that is what we have here, negative ds dP. And in this case, pressure was constant, so in this case, temperature is one which is going to become constant. So that is what you are going to have for the second derivative for the two equations. So we have this one for the first, for A, and this other one for B. Now, when you compare the two second derivatives, you can see that the difference between this portion and this other portion is not there at all. What is different is this part, dV dt, pressure constant, and negative ds dP. So this portion and this other portion, they are the same. It's only that if you interchange the conditions that were put here, if you interchange these conditions, that is, if you make this one T and this one make it P, is definitely you have the same, this one being the same as that. So if that is the case, then it means that what is the difference between the two second derivatives is what we have here, dV dt, pressure constant, minus ds dP, temperature constant. And therefore, that is how we come to this conclusion here, that if this one is the same, then it means also this part is also the same. And that's why we are saying dV dt, pressure constant, is equal to negative ds dP, temperature constant, is equal to this negative ds dP, temperature constant. And ladies and gentlemen, that brings us to the end of this second video on deriving Gibbs free energy Maxwell relation. So I hope it has brought some light on whatever you're not able to understand from the notes. Thank you.